Hello and good time, everyone. With the current advancement in AI technologies, when it is that a lot of organizations started to use AI-based tools for decision making, this is because decision making using AI tools is objective and it avoids the subjectivity of human decisions, and also that computers can process a lot of data in a short time. However, we need to make sure that these decisions that are made by the machine learning or by the AI-based tools are fair and they are not discriminating against specific individuals or subgroups of the community. This is why we decided with my student, Bigum Hatatolo, and my colleagues, Hassan Kaya and Dianis Veligerakis, to develop a tool called SynthFair, for ensuring subgroup fairness in classification, and it is called SynthFair because it's based on synthetic data generation. So initially, if we look at the reports that has been exchanged through the media, there were a lot of reports about big systems that showed to be discriminated against specific groups or specific individuals, such as the same-day delivery by Amazon and the AI recruiting tool that was developed by Amazon, which both of the systems, they were multi-million projects, and also the Compass recidivism tool that is used, or system that is used in multiple courts in the US. And these systems, they all has been discovered to be discriminating or to provide unfair treatment for specific individuals. But is that important? Why this is so important? It is, if not that is not ethical only, but also some of the organizations can be fined with big penalties, such as the Bank of America, which has been fined 335 million for minority discrimination. And that is not the only organization. There are a lot of big companies that has received fines with multi-million US dollars. And these fines are applied to these companies that I think these ratings or these reports from 2019 or we can see what is fair actually, or how can we make sure that there is a fair treatment or not. So the generic definition for fairness is the absence of prejudice or favoritism towards individual or groups of the community on their intrinsic or acquired traits in the decision-making context. However, this cannot tell us exactly what can be considered as, or to give us a quantitative approach of what can be considered fair or not. But it is saying that it can give hints that, okay, don't use the sensitive attributes or some of the attributes that the humans or the individuals cannot change in their own, because they have been born with this with these characteristics or so. So the human rights already identified a set of attributes or characteristics that shouldn't be considered when making a decision on for specific individuals or for specific groups, and these are called the protected characteristics or the sensitive attributes in some cases, and include age or disability, sex, race, and marriage and civil partnership, and so on. So why these machine learning techniques can be biased? The fact is that these machine learning techniques cannot be biased by their own, but the bias can be as a result of the data that they are trained on. And the sources of this bias could be historical bias or labeling, when this decision has been made by humans at the first place, and these decisions might be biased or subjective to the person who took the decision, or also because of the limited or less informative features that cannot provide the machine learning technique with the amount of information that they require to learn a good classification or a good prediction. Also, biased data collection, when you collect the data from specific groups or from specific individuals, and also imbalanced representation of the different demographic groups is also one of the reasons. However, how can we say that as I mentioned earlier, that the definition, the generic definition for fairness cannot tell us quantitatively how can we say that this algorithm is fair or not. So there are specific set of fairness measures that has been developed by researchers, and these fairness measures include start by dividing the community into demographic groups and identify favorable class label, which is the class label that we would like to receive all of us. Then they identify two types of groups in the community. They are the privileged and the unprivileged groups based on the decision label. So if they are receiving more higher rate of the favorable class label, then they are considered as privileged, and vice versa. And these algorithms or these fairness measures can be divided into group fairness measures and individual fairness measures. So first, before looking at the notations or the formulation of these fairness measures that can tell us to what extent a specific algorithm or specific data set is fair or not, or biased or not. So first, we look at some of the notations. So we are assuming that the data set that we have contains set of different types of features. These features include X, which represents the set of attributes that contains no sensitive information. S, which is the set of sensitive attributes that contains sensitive information. And Y is the class label. And the class label, we use Y for the class label, for the actual class label, Y hat for the predicted class label. And these class labels, we consider them to be from a binary or to be a binary, positive and negative, or favorable and unfavorable class label. And also we define two groups, or consider that there are different groups. So one of them is privileged, the highest privileged, and the other is unprivileged. And we denote them by G and G prime. So how can we quantify fairness? There are a lot of different techniques or measures that can tell us how fair a given data set or the outcomes of a machine learning model. That includes demographic parity difference, where we are taking the difference between the rate of receiving the favorable class label for the unprivileged group with the rate of the receiving the favorable class label from the unprivileged group. If this difference in the rate is close to zero, that means the algorithm or the data is fair. If it is deviating from zero much, then this is unfair. However, the definition of much is still problematic somehow. There is the other technique, which is the disparate impact ratio, which looks at the ratio between receiving the favorable class label for the unprivileged group with the rate of receiving the favorable class label for the privileged group. And then if this ratio is greater than 0.8, according to a rule in the labor law in the US, then this technique or the data or the algorithm will be considered as fair if this ratio is greater than 0.8. And in similarly less than 1.25. And there is an individual fairness measure, which is called consistency. And in the consistency, we look at the decision that is received by individuals and compare this decision to the decision that are received by the nearest neighbors for this individual, and take the average over all of these individuals, and this will give us the consistency. If this value is close to 1, that means the algorithms or the data is not biased, it is fair. If it is much less than 1, then in this case, we consider this the data or the machine learning model to be biased or discriminating against the individuals. However, now we learn about this the group and the individual fairness measures. How can we mitigate the bias that exists in the data? So there are a lot of bias mitigation algorithms, and these mitigation algorithms can interact with the machine learning pipeline. So we have here, this is a typical machine learning pipeline where you have training data, you train a model, you get that model, then you have unseen data, you perform prediction and get the outcomes. These different bias mitigation algorithms work in different stages of this the pipeline of the machine learning model. So some of them, they change the data or try to remove the bias before training the model, which is called pre-processing algorithms, including the disparate impact removal, learning fair representation, and so on. And in the other case, there are some of the in-processing algorithms that are trying to optimize the algorithm itself or the machine learning model to be fair during the training process. However, these algorithms need simple classifiers to be working on, because it will be hard to improve fairness or to interact with in symbols, for example, like random forest or gradient boosting trees or neural networks. However, most of these techniques are working with logistic regression and decision trees, and including, for example, adversarial debiasing and so on. And the third type of bias mitigation algorithm is post-processing, which interact with the data after performing the predictions. So it looks at the outcomes. If the outcomes are fair, then that is good. If the outcomes are not fair, then the algorithms will decide to change some of the labels. And that might be a little bit problematic or ethically problematic, because assuming that you predicted, or there is a person or individual who should receive the favorable class label, and then this algorithm goes and decide that this individual need to receive the unfavorable class label. However, for our SynthFair, it is a pre-processing model, and so which means that we are interacting with the data before training the model, and this is based on specific assumptions, so that we are assuming that the source of the bias that exists in the outcomes of the machine learning model is based on the different levels of representativeness of the groups or demographic groups in the data, especially when we are thinking or talking about receiving the favorable class label. How do we perform this, or how we force fairness, is by forcing the machine learning model to predict more favorable class labels for the minority group or for the unprivileged group. And we do that by generating more synthetic examples, such that we have more examples from the unprivileged group that are receiving more favorable class label, and because of that, the machine learning model will learn to predict more class label, favorable class label for this group. So this is the pipeline of our system, which starts, it's the typical pipeline. So we have the data, then we pre-process the data, split it into training and testing. However, then we train the classifier and perform the predictions. However, the new things that we perform is that we cluster the data after the training set, after the split, and then get these different clusters or the parameters for these clusters. Then within each of these clusters, we generate synthetic examples such that we balance the number of representatives that exists from each group or that are represented in this cluster, such that each subgroup will have the same number of positives and the same number of negatives within this cluster. And then we train the classifier and perform the prediction. We have also, when we train the classifier, we are training either a single classifier or multiple classifiers. So either we combine all the clusters in one big data set, training set, and then we train one classifier, or we train multiple classifier such that each classifier is trained using the data from one of these clusters. So for the synthetic data generation, we use two techniques. We use SMOT, which is a statistical technique, where you take two examples from the group that you would like more examples from that group, and then perform linear interpolation between these two points that are close to each other. So you pick randomly one example, and then look at the k nearest neighbors, and then decide on this k nearest neighbor to generate more examples between these examples. The other technique is the generative adversarial network, which consists of two networks, the generator and the discriminator, and they are playing this zero-sum game where the generator is trying to predict or to learn the patterns from the original data and generate synthetic examples, and then the discriminator will try to figure out if this example is fake or real. And they continue this until they reach at an equilibrium. However, SMOT will give us more flexibility to decide in which regions we are going to sample more examples, while in GANs we have no control. We train the networks, and then the networks will learn the patterns in the data and generate the examples based on this, the learned models. And then we have our technique where we are, as I mentioned, in the training for the classifier. So we train either one classifier by combining all the clusters from with all the data sets that we generated or the data examples that we generated, and then we train a single classifier M, or we train k classifiers according to the k clusters that we provided or that we identified. And these k classifiers can be used for the predictions. During the prediction, we have three strategies. The first strategy is associated with the case when we train only one classifier, where the class label, we have only one model. So the predicted class label will be the outcome of this model when it receives this data sample. The second strategy is to look at the distance between this example to the centroids of the different clusters, and then use this distance as weight for the decision that is made by each one of these models, and then combine this based on this equation, which is taking the weight of this classifier based on for each classifier that is trained on a specific data set from one of the clusters. The third technique is that we take the decision based on, first, we look at the example and assign it to the closest cluster, which is cluster CI, for example. And then we take the decision, which is y hat equal the mi of x. There is a typo here. There's this omega w, which is not necessarily not needed. So the decision is made by mi, where when we are assigning this x to the cluster, it assigned to cluster CI. So for evaluating our technique, we evaluated our technique using three benchmarks that are well known for comparing or for evaluating fairness algorithms: adult, German, and Compass. And here are the characteristics of the data, including the class labels and the favorable or the privileged groups and the sensitive attributes. When we compared first the three techniques, the three strategies with GANs, and we noticed that in some cases GANs are outperformed the methods. So for example, for the consistency, we can see that GANs is working better. For some cases, we can see strategy 1 and strategy 3, but strategy 3 showed in 2 cases that it is doing better with gradient both increase. So we are recommending to use strategy 3. And in comparison with baseline methods, we noticed that we compared with learning fair representation, which is pre-processing technique, and adversarial debiasing, which is in-processing technique. And we can see that in most of the cases, our technique is performing a little bit better than the others. and outperforming the other techniques in improving fairness. So to conclude, we propose SynthFair, which is a pre-processing technique for bias mitigation that is based on synthetic data generation. So we examine two techniques for generating the synthetic data, which are the smooth and the generative adversarial networks. We propose three strategies for predicting the labels of the test examples using models trained on the enriched data. For the future, we are working on making a better decision on the regions where we can generate more examples. So if you have any questions, you can send them by email. Thank you, and sorry that I wasn't unable to attend the conference in person. However, this is my email, and this is the GitHub repository if you would like to try the code. Thank you, and have a good day.